chasing waterfalls.
Welcome again to today's class. In this video, we want to discuss the topic quantum number. This is an important topic in the subject chemistry. Yes. And so we want to discuss all the concept, everything about it, so that we'll learn from it as well. Now, let's see the definition. Quantum number is defined as a set of numbers used to describe the position, the energy, and the spin of an electron in an atom. Yes. We have four quantum numbers in the field of chemistry. One is principal quantum number, two azimuthal or subsidiary quantum number, three magnetic quantum number, and four spin quantum number. Let's write it down. One, principal quantum number. Q mean quantum, N mean number. Two, azimuthal or subsidiary quantum number. Three, magnetic quantum number. And four, spin quantum number. So these are the four types of quantum number we'll discuss in this video. We'll start it one after the other. One, principal quantum number. You may have heard a lot of things about this quantum number, so let's recall some of those points you know before now. Principal quantum number discusses the energy levels of an atom. It describes the energy level of an orbital. It also discusses the maximum number of electrons in the shell of an atom. It also discusses the maximum number of electrons in the shell of an atom. And that is why it says that the formula we use to get the maximum number of electrons in the shells of an atom is 2n raised to the power of 2. That is the formula the principal quantum number gave us, where n is talking about the number of what? Orbitals. The number of orbits or shell. Number of orbits or shell, which is described with the letter K, L, M, N, etc. This is for when it is first shell, second shell, third shell, and fourth shell. This means that the principal quantum number describes the size of an electron orbital. It describes the size of an electron orbital. That tells you that when the value of n is high, the energy level of an orbital will be high. The maximum of electron in an orbital will be high, or the maximum of electron in an orbit or shell will be high. You get? And so that is what you talk about. Look at what we mean. When n is equals to 1, we put it here. 2, 1 raised to the power of 2. The answer will give you what? 2. That means that for the first shell, it will have maximum of 2 what? Electrons. And that is what we call duplet structure. Duplet structure simply means that the highest number of electrons the first shell should have is 2. Okay? Then, when n is equals to 2, we say 2 bracket 2 raised to the power of 2. That is this. We have this 2 inside the bracket is the number of orbits or shell. That will be giving you 8 electrons. And so the second shell should have 8 electrons. Do you notice that the number of electrons increases as the value of n increases? Yes. That is why we say that the value of n, once it increases, the maximum of electron in the shell must be increased. That is one. Then the energy of that electron will be also what? Increase. Then we also say that the size of the electron orbital will also what? Increase. So both the maximum number of electron, the energy, and the size of the orbital all must increase once the value of n increases. Okay? Then when n is equal to 3, it tells you that 2 bracket 3 raised to the power of 2, that will be giving you 18 electron. Okay? Now, are we going to assign 18 electron in the third shell? That is the question. No is the answer. The rule of this way of sketching it says that the first shell will have maximum of 2 electrons, whereas the subsequent shell will have maximum of 8 electrons. Now, if we go by that rule that the subsequent shell will carry maximum of 8 electrons, the question is, what happened to the remaining 10? Where are we going to locate it? This is one of the things principal quantum number using this pattern did not explain. How to assign your full 18 electron. It didn't explain it. And also, when n is equal to 4, 2 bracket 4 raised to the power of 2 will give you what? 32 electron. Remember, this subsequent shell or orbit should have maximum of 8. So assigning 8 here, where will be 24 remaining electron be located? This did not explain it. And this is what the azimuthal or subsidiary quantum number and magnetic quantum number will help you to appreciate what happened to those electrons. Remember, we've discussed what principal quantum number talk about, the energy of an orbital, the energy level of an orbit or shell. He also discusses the maximum number of electrons in an orbit or shell. He also discusses the size of an electron orbital. And he also gave us a formula for getting maximum number of electrons in an orbit or in a shell. And that is 2n raised to the power of 2. Now, we go to azimuthal or subsidiary quantum number. We want to see what he explained. First, azimuthal quantum number tells us the shapes of an orbital. Not only that, he also explained the subshells of an orbital, the subshells of an orbital and the orbitals in it, and how those electrons, which we didn't see how it is being assigned in the third and the fourth shell, how they are being packaged and how they are being assigned in the subshells. Let's see what we mean by subshell. Okay, first of all, it describes the shapes of an orbital, and we said that the orbital he mentioned is S, P, D, F, G. The S own is spherical shape. It has a spherical shape, while this one has dumbbell shape. The B own have dumbbell shape. The D own has a double dumbbell, and the F own complex geometry. The F and the G own are complex geometry. That is their shape. Okay, now after talking about this shape, this azimuthal or subsidiary quantum number says it is denoted with L. It is denoted with L, whereas the principal quantum number is denoted with small letter n. That is why we talk about number of electron in the shells of an atom. So it's talking about the shells of an atom, whereas this one discusses what happened in the subshells. What happened in the subshells? What happened to the orbitals in the subshells? What are the orbitals in the subshell? Okay, let's see. This L ranges from 0 to n minus 1. It ranges from 0 to n minus 1. That is what the azimuthal or subsidiary quantum number tells us. What do we mean by it ranges from 0 to n minus 1? Okay. When n is equals to 1, that is in the first shell, our L will be equals to what? It starts from 0. 1 minus 1, 0. So we will have only one value of L. Now, that one value of L is called s orbital. That means when you are talking about s orbital, you tell us that the azimuthal quantum number of it is 0. That is what it means. When n is equals to what? 2. We say that our L will ranges from 0 and stop at 2 minus 1, 1. So it will start from 0 and stop at 1. This is what we call s orbital and p orbital. That means when L is equal to 0, it's talking about s orbital. When L is equal to 1, it's talking about p orbital. Yes. Okay. Then we also say that when n is equals to 3, when n is equals to 3, our L will be equals to 0, 3 minus 1, 2. And so we can't just count 0 and enter 2. 1 will follow before 2. Because it ranges from 0 to what? n minus 1. So 3 minus 1 is what? 2. So this will be called s orbital, p orbital, and what? D orbital, according to this pattern. Then when n is equals to 4, okay, our L will be equals to what? 0, 1, 2, 3. This is s orbital, p orbital, d orbital, and f orbital. Now, that is how you continue. Let's see how we can appreciate these things we are talking about. Oh yeah. In the first shell, we said that according to principal quantum number, that the first shell says it will have maximum of what? 2 electrons. Yes. Now, according to azimuthal or subsidiary quantum number, it says that the first shell will have s orbital. Okay. This n is 1. This is 1. This is s, the orbital itself. Yes. So that means the subshell inside the first shell, which is this shell we are looking at, the subshell inside it is called 1s. 1 what? S. 1 means n is 1. S means the orbital is s. Then for the second shell, okay, we also said that it has 2 what? Orbitals in the second shell. What do we mean? N is 2. I will write 2. The first is s. The first shell is s, comma. N is 2. The second orbital is what? P. So the first orbital is s, while the second orbital is p. That is what is located there. That means that this is the what? Subshell in that what? The shell you are talking about. In the second shell you are talking about, this is subshell, this is subshell. You go to this third one. We also said that in the third one, the third shell, we have 3. That means 3s, 3p, and what? 3d. Okay? In the first shell, we will have 4s, 4p, 4g, and what? 4f. Can you see it? Yes. And that is how you do for the fifth shell, and also have L to be 0, 1, 2, 3, and 4. Place and place. The value of n should not be equal to L. That means if n is 4, you shouldn't have 4 included. If you have 4 included, we say in chemistry that the orbital is mechanically what? Forbidden. And so you shouldn't have L equals to 4 here. Okay? If you have any question, please use the comment box in the description below and ask your question. I will attend to it. Okay? Now, we have been able to locate the subshells in the orbital. These are the points where the electrons we are looking for, or we are trying to see. This is where they are to be fixed themselves. They are to be located. And so, how do we do that? According to azimuthal or subsidiary quantum number, it says that number of orbital in a subshell number of orbital in a subshell is equals to 2L plus 1. Please note this formula. Number of orbitals in a subshell is 2L plus 1, whereas maximum number of orbital in a subshell is equals to 2 bracket 2L plus 1. Okay, look at what we mean. If we are talking about this first subshell 1s, number of orbital s we have, which is used while writing electron configuration of an element using Hall's rule. The number of orbital in that subshell, which is on the orbital s, number of orbital here is s has L to be 0, 2 times 0, 0 plus 1, 1. That means it will have, for X, it will have 1 orbital. Then for P, number of orbital in subshell, any subshell having P, like 2P now, number of orbital in that orbital P is 2 times L for P is 1. 2 times 1, 1 plus 1. 2 times 1, 2 plus 1, 3. 3 orbitals. This is what Hall's rule make use of while writing the electron configuration of an element using Hall's rule, where you be seeing for S 1 orbital, for P 3 orbital, and so on. Let's see the D on. D is represented with L equal to 2. So we now say 2 times 2, 4 plus 1, 5. We say it's 5 orbitals. Then F on. F is 3. 2 times 3, 6 plus 1. That is 2 times 3, 6 plus 1. That is 7. 7 orbitals. So guys, this is how Hall's rule come up with his orbital principle, that S will have 1 orbital, P will have 3 orbitals, D will have 5 orbitals, F will have 7 orbitals, and so on. Okay? Then maximum number of orbital, maximum number of electron in an orbital. Maximum number of electron in a subshell or in an orbital. So maximum number of electron in an orbital in a particular subshell or in a subshell orbital in bracket is 2 bracket 2L plus 1. Look at what we mean. In this subshell, it has orbital S. Maximum number of electron here when you talk about S is 2 times 1. You have it to be 2. Then S is 2. Then for P, that is 3 orbitals. Okay? Maximum number of electrons in a subshell. Remember, what you see here is what you see here. So times 2 is what we are now doing. You say 2 times 3. Every P we have 6. Why every S we have 2? Because 2 times 1 is 2. Then for D is 5 orbitals, right? Maximum number of electrons in that orbital will be 5 times 2, 10. 10. 10. The B is 6. And the F, let's see F. F is 7 orbital. Maximum number of electrons in an orbital of that subshell is 7 times 2. That is 14. Okay. We have seen now how to get the subshells which has their orbital in it. Subshells of a particular shell. This is how to get the subshells of a particular shell, and each of those subshells will have its orbital. So this subshell have S with maximum of 2 electrons. This one S with maximum of 2 electrons, and what? P with maximum of 6 electrons. How did we get this one? One means we are talking about first shell. These 2 and these 2 means we are talking about second shell. This 3 means we are talking about third shell. Then this 2 electrons, 6 electrons, 10 electrons, we got them from this formula. Then fourth shell, these 2, 6, 10 and 14 is gotten from number of orbital in a subshell and maximum number of electron in a orbital of a subshell. Okay, that is how we got this. I believe you understand what we are saying. So if you have any question, make use of the comment box below and ask your question. I will reply you. Okay. Now we have been able to see what azimuthal or subsidiary quantum number could explain and how it could take care of what this principal quantum number couldn't explain. Okay, you have seen that here principal quantum number could not explain where this remaining 24 electron in that fourth shell is assigned, where the remaining 10 electron in the third shell, because we put 8, it remained 10. We put 8, it remained 24. It couldn't explain where they are assigned or what happened to those electrons. But the azimuthal quantum number has helped us to see what happened there. Okay, let's also see what magnetic quantum number also talk about. Under magnetic quantum number is talking about the total number of orbitals in a subshell. The total number of orbitals in a subshell and the orientation of these orbitals. Yes, this magnetic quantum number also help us to see how this electron we are looking for, on how they are being assigned, how they are being assigned to this shell. It also discuss how to do that. Now, let's see what it says. Magnetic quantum number says is represented with M, and it ranges from -S, L to what? Plus L. Yes, that means that if we are talking about n equals to 1, if we are talking about n equals to 1, we will see that L will be equals to 0 and M will be equals to minus of 0 is 0 and plus of 0 is 0. Remember how we got this L. We said that L means it starts from 0 to n minus 1, and 1 minus 1 is 0. So we have it like this. We'll just discuss it now. Okay. When n is equals to 2, we said that L will be equals to, it ranges from 0 to what? 1. Right? Then what we now say is that for m equal to 0, we will say that for m equals to 0, for L equal to 0, it will have m equals to 0. And for L equal to 1, it will have -1, 0, and +1. That means it ranges from -L to +L. So we have to do the one of L equal to 0 first. do for L equals to 1, we have gotten for M equals to 2. Then for N equals to 3, we also say that L will be equals to 0, 1, and 2. Okay? Therefore, M will be equals to what? 0. When L is 0, M will be equals to minus 1, 0, and plus 1 when L is equals to 1, and also M is equals to minus 2, minus 1, 0, plus 1, and plus 2. So that is how you also do it for the one of N equals to 4. You also get it. Now, it is important to see how this explains the electron we are looking for in this principal quantum number. For N equals to 1, L equals to 0, M equals to 0. So how many M do we have? Only one M. One value of M times 2 will give you 2 electrons. For N equals to 2, L equals to 0 and 1. What is M? M is 0 when L is 0. M is minus 1, 0, and plus 1 when L is 1. And so total is 1, 2, 3, 4. So you say 4 times 2 equals to 8 electrons. That is about second shell. For third shell, N is equal to 3, L equal to 0, 1, and 2. For L equal to 0, M is equal to 0. For L equal to 1, M is equal to minus 1, 0, and plus 1. And for L equal to 2, M equal to minus 2, minus 1, 0, plus 1, and plus. So this is according to number line. Minus 2, minus 1, 0, plus 1, and so 1, 2, 3, 4, 5, 6, 7, 8, 9. So we now say this is 9 times 2 equals to 18 electrons. That is how you do for the one of fourth shell. So I would like you, the audience, to do the one of fourth shell and see whether it will give you 32. Please, if it gives you 32, tell me yes in the comment box below. It gave you 32. But if it did not give you 32, also tell me no, it didn't give you 32, so that we can sort it out. Okay? So this is about magnetic quantum number. Magnetic quantum number. And so we've seen how magnetic quantum number also explains what happened in principal quantum number. Like this, when N equal to 3, that we said we assign 8 and we remain 10, and we are asking what happened to the 10. We couldn't explain it. We could explain what happened to it. That means this is the label, the name of the orbitals, the names of the orbitals that are available when N is equal to 3. Okay, so we are seeing how it gives us total of 18 electrons. Now we go to spin quantum number. Under spin quantum number, we say that spin quantum number describes the angular momentum of an orbital. Yes, it describes the angular momentum of an orbital, and it's denoted with S, letter S, which is plus half and minus what? Half, which is plus half or minus half. You use plus half when we are talking about upward spin, and we use minus half when we are talking about downward spin. This is where we go into Hall's rule to see how we can assign these spins. We will be able to get this information clearly. Okay, that is about these 4 quantum numbers we have. It is important to note that if one is asked to get the magnetic moment of a particular element or ion, please, the person should use the formula magnetic moment equals to square root of n bracket m plus 2 Bohr magnitude, where n is equal to number of unpaired electron. Number of unpaired what? Electron. Okay? Number of unpaired electron, you could see when you draw the electron configuration of that element using Hall's rule. Okay? Now, when the magnetic moment of a particular element or ion is 0, what is it trying to tell you? Since we say where n is number of unpaired electron, that means the number of unpaired electron there is 0. It doesn't have any unpaired electron. So we say no unpaired what? Electron. No unpaired electron. And so we call it diamagnetism. Okay? Then when the magnetic moment is not 0, when it is not what? 0, what we say is that there is unpaired electron. The implication is that there is unpaired electron, and that is what we call paramagnetism. Paramagnetism. That is when it is not equal to 0. When magnetic moment is not equal to 0, we say it is paramagnetism. When we go into question solving, you understand it. Now, the element itself whose magnetic moment is 0 is called diamagnetic element. Diamagnetic element, that means it has no unpaired electron. That is about English coming in. Whereas the element whose magnetic moment is not equal to 0, we say they are paramagnetic element. That is, they have unpaired electron. For this one, they have unpaired electron. That is why we call it paramagnetic element. Whereas this one, it has no unpaired electron, and that is why we call it diamagnetic element. So the phenomenon is called diamagnetism and paramagnetism. It is important to note from here, the first one is 1s2, right? The second one is 2s2. The third one is 2p6. The fourth one, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14. Now, look at this as we write another one. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 3d10, 4p6, 4p6, then etc. etc. We are looking at something now. In the first one, we stop at 4p6. In the second one, we stop at 4p6. Look at it critically well and know whether these two things are the same. You will notice that at this point, they are not the same. But the question is, which of these two are correct? We got this from what we got here, and we got this from another way. But the question is, which of these are correct? That takes you to rules called energy rule. Energy or M plus L rule. What does this energy bracket M plus L rule states? 1. It states that electron will enter into orbitals of lower value of energy first before entering into orbitals with higher value of energy. It also says that if you have, for instance, two orbitals with equal value of energy, if you have, for instance, two orbitals with equal value of energy, what will happen is that the electron will enter into the one that have lower value of n first before entering into the one with higher value of what? N. So first, electron will enter into the one of lower value of energy. Value of energy first. First, before entering into the one, into the orbital of higher value of energy. Okay? And when two orbitals have equal value of energy, electron have to enter into the orbital with lower value of n first before entering into the one of higher value of n. Okay, let's see what we are talking about. The L of S is 0. The azimuth that is L of S is 0. And this one is N of this S. So 1 plus 0 is 1. 2 plus 0, 2. 2 plus 1, 3. 3 plus 0, 3. 3 plus 1, 4. 3 plus 2, 5. 4 plus 0, 4. Then 4 plus 1, 5. etc. Okay. Which one should come first? The one of 1s2 because it has lower value of n. We have added n with the L, n with the L, and it gave us this. Now we are seeing the one with lower value of energy because it says electron will enter into the one of lower value of energy first before entering the one of higher value of energy. Okay. This follows with 2, that is 2s2. It follows with 3, that is 2p6. It follows with 3, that is 3s2. They follow with 4, that is 3p6. Then look at another 4. This 4 is owned by which one? This 4, this 3p6, this is the one of 5, and this is one of 4. That means I'm to write this one first because it is 4. 4s2. Then write this one 3d10. Then write this one 4p6, and it continues that way. That means that this is the best way of writing electron configuration of an element. That is with use of energy rule, which says electrons have to enter into orbitals with lower value of energy first before entering into orbitals of what? Higher value of energy. And if two orbitals have equal value of energy, electrons have to enter into the one with lower value of n first before entering into higher value of n. Okay? And that is how we come up with this. Now, that will tell you that the energy increases this way. Energy increases this way. This energy of this orbital is higher than this. The energy of this is higher than this. The energy of this is higher than this. That is what it means. So it is important to know that if the energy is high, this is about energy. It will be what? Less stable. If the energy of an orbital is high, the implication is that the stability will be very low. So the higher the energy is, the lower the stability. Do you get it? And if the stability is high, that means the energy will be what? Low. The higher the stability, the lower the energy. And the higher the energy, the lower the stability. Please have to know this because these are possible questions they can ask you on this. So we've been able to see how to write electron configuration of elements And we have been able to see how to calculate energy rule or energy quantity of an orbital. That means add the n, which is the number written by the side, with the value of L. For S, L value is 0. For P, L value is 1. For D, L value is 2. And for F, L value is what? 3. So S, L value is 0. P, L value is 1. D, L value is 2. And F, L value is 3. So you have to note it. We wrote it somewhere here. We wrote it somewhere here. So note it, the values of their L. So you just be adding it with the value of N individually to be able to get the energy and be able to sort it this. Okay? So next is we will go into important questions, important calculations under this. That means they can ask you question on the energy and stability of an orbital. Remember, the higher the energy, the lower the stability. They can also ask you the electron configuration of an orbital. But it's important to note that electron configuration of an element is said to be stable if the p and the d orbitals are half-filled or fully filled. So we said that the electron configuration of an element is said to be what? Is said to be stable if the p and the d orbital part is half-filled or fully filled. Yes, we will try to understand it. That is, if we have p raised to the power of 3, or if it ends with p raised to the power of 3 or p raised to the power of 6, then, or if it ends with d raised to the power of 5 or d raised to the power of 10. If the electron configuration of that element ends with p raised to the power of 3, that is half-filled or fully filled, or d raised to the power of 5 or fully filled. It depends on the element we talk about. That means the element that will be ending with p, you stop at p, filled or fully filled, and the element that will be ending with d, you have to stop at half-filled or fully filled before you say it is what? A stable electron configuration of that orbital. So we will go into question solving. Here are some of the questions we want to look into in quantum numbers. Number 1, find the magnetic moment of A, copper 2 ion, and B, beryllium. Okay, let's see. To get the magnetic moment of this, we said that magnetic moment is equals to square root of n bracket n plus 2. And the unit is Bohr magnitude. Yes. So when you have the electron configuration of that element, then you cannot have the magnetic moment of it. Let's see what we mean. Okay. For copper 2 ion, we have it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Yes, we stop at 3d9 because copper has 29 electrons. Copper has 29 electrons. So this is electron configuration of copper, so to speak. And so, what do we mean by copper 2 ion? Copper 2 ion simply means that copper as a metal is going to lose 2 electrons. From where? From the outermost shell. What is the outermost shell of copper in this electron configuration? Please, I want to ask, why we were sketching this electron configuration of elements in our first video on quantum numbers, you notice that 4s represents when n is 4, and 3d represents when the shell is the third shell. So 4s is on the 4th shell, 3D is on the 3rd shell. Now, if this is your 3rd shell and this is your 4th shell, for instance, and this is your 4x2, and this is your 3D9, because 3rd shell must be inside the 4th shell. Now, I want to ask, should the electron leave from the innermost shell or from the outermost shell? You and I will believe or have this belief that electron always leave from the outermost shell. So what is your outermost shell? That is 4s2. So this 4s2 you are seeing, these 2 electrons here will be lost. And once it is lost, what we will be having here is 4s raised to the power of 0. That means the s orbital has no electron anymore. So that means 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d9. That is for what? Copper 2 plus. So as it is like this, is unstable. It's an unstable element because this d orbital is not half filled or is not fully filled. Remember we said when d orbital is half filled or fully filled, the electron configuration is noted to be a stable electron configuration. And also if p orbitals, if they are half filled or fully filled, and if d orbitals is half filled or what? Fully filled, we said that that electron configuration is said to be a stable one. So this is not a stable one because it neither half filled or fully filled. So it is unstable copper 2 ion. Whether it's stable or not stable, it doesn't concern us as we want to talk about magnetic moment of it. Okay. Now, after noting this, you will notice that this is what? This is one orbital from the formula 2l plus 1, number of orbital. S is noted to be L equals to 0. When you are talking about s orbital, we say that L is equals to 0. So 2 times 0, 0 plus 1, 1. So one orbital will be for this one s. Then for this one, we say it is what? One orbital because it's still s. For the p, we say it is what? 3 orbitals. 3 orbitals. Then for this one orbital because it is s. For this, 3 what? Orbitals for the 3p. Then for this one orbital, which nothing is there. So there is no electron here. So there is no need of wasting our space. Then this one, d, is 5 orbitals. 1, 2, 3, 4, 5. All this will be paired because they are 2s. Paired. That is what we'll talk about, that spin. We say upward and downward spin. Paired. Then this one paired. This one still paired. Now come to this 3d9. It will enter singly first because it is not up to 10. It will enter singly, then before what? Pairing. 2, 4, 6, 7, 8, 9. So you now see that it has only one unpaired what? Electron. Are you getting it? It has only one electron. Remember how we noted that this day we have 5 orbitals. We said D from S, P, D, F. This is 0, 1, 2, 3. So D has L to be 2. 2 times 2, 4 plus 1, 5. That is how we noted to be 5. So it has only one unpaired what? Electron. And because it has only one unpaired electron, we will now say that the formula m bracket n plus 2, magnetic moment of it will be equals to what? Square root of n bracket n plus 2, and it will give you, where n is number of unpaired electron, that is, how many orbital has electron that is not unpaired? I mean, how many orbital has electron that is not paired? How many orbital has unpaired electron? We have only one orbital that have unpaired what? Electron. So one unpaired electron. So we now say square root of 1 bracket what? 1 plus what? 2 equals to 1 plus 2, 3. 3 times this, square root of 3 equals to 1.73 Bohr magnitude. The unit is Bohr magnitude. Yes. Now, because it has value for magnetic moment, because it has value of magnet, that is, the magnetic moment is not zero. Once magnetic moment is not zero, the implication is that from the electron configuration of that orbital using Hall's rule, it has both paired and unpaired electron. And in this case, the unpaired electron it has will now overshadow the paired electron. And that is where the principle of paramagnetism came in. Paramagnetism came in. That electron configuration of that element has both paired and unpaired electron, where the unpaired electron will overshadow the paired one, hence called paramagnetism. Okay, so because it has a value for magnetic moment, that is, the magnetic moment is not zero, we call it paramagnetic element. Paramagnetic element or paramagnetism as a phenomenon. Okay. Now, for the question number 2, beryllium. Beryllium. It has how many electrons? 4 electrons. 4 electrons. That means 1s2, 2s2. Wow. That is how it goes. So this is one orbital, and this will be what? Paired. Because it's filled. So this is paired, this is paired. How many unpaired orbital does it have? How many unpaired orbital does it have? No. Everything is paired. Each of the orbital, the elements there are what? The spin there are paired. So no orbital is unpaired. And because there is no orbital that is unpaired, we say that n will be equal to 0. Number of what? Unpaired orbital is what? 0. Therefore, magnetic moment will be like a 0 plus 2. 0 plus 2 is 2. 2 times 0 is 0. Square root of 0 will be what? 0 Bohr magnetism. That is where the name diamagnetism comes in. That is, beryllium is a diamagnetic element. Why? It only have paired electron. It only have paired electron and no unpaired electron. And because it has no unpaired electron, it means that unpaired electron of it is 0. And so it will be called a diamagnetic element, or principle of diamagnetism will come in there. That is about question number 1. I believe you understand it very well. And so if you do not understand any point of it, aspect of it, please make use of the comment box below and ask your question. Thank you. We go to question number 2. We say, what is the maximum number of electron orbital? What is the maximum number of electronic orbital with the following set of quantum number? Watch. For A, we say the formula is what? 2 bracket 2L plus 1. Where L is 1, 2 times 1. 2 bracket 2 times 1, because L is 1 plus 1. Okay? And so what it will be giving you? 2 plus this, 3 times this, 6 electron. Yes. That means that this is talking about what? P orbital. P orbital. That means it's talking about 2p what? 6. This shell 2p6. That is why we have 6 electrons. 2p6, where n is 2, p is L equal to 1 and 6 electrons. Then for B, wow, n is equal to 3, L is equal to 3. Please don't just say 2 times 3, 6 plus 1, 7, 14. Please don't try that, because you see value of L. We said that when n is equal to L, when the value of n is equal to L, the implication is that the orbital is mechanically what? Forbidden. It's mechanically forbidden, so we don't have such. This is mechanically forbidden. We go to question number C. We say that this is less than this. Yes, L must be less than n for you to have for the orbital to exist there. So for it not to be mechanically forbidden, L must be less than n. Okay, we now say that the formula is 2 bracket 2 times our L is 2 plus what? 1 equals to 2 times 2, 4 plus 1, 5, 5 times 2, 10. That means this is talking about 3. L is 2 and it's talking about d orbital. Okay, 3d what? 10. 3d10. That is the subshell that is talking about. We go to the next one. Write the stable electronic configuration of copper plus 1 and what? Copper zinc 2 plus. Electron configuration. For you to be able to write it well, please and please do not forget what I've been saying, that for electron configuration of an element to be stable, the P should be what? Half filled or what? Fully filled. That is P3 or P6. Or D is half filled or what? Fully filled. This is the cases that are involved. Okay? Okay, so what we will do here is we now say for copper. Look at for copper. We have drawn it before now. Now, for us to say that that copper is a stable electron configuration, one element from 4s2 will jump and enter this d orbital to make it 10. And so we'll be having it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s1, 3d10. That is electron configuration of copper. That is for copper. Yes. Remember we said it must obey the rule that either it is half filled or fully filled for P and D orbital part of it. So because the D ends at 9, this will move from 1. One electron will move from this 4s2 and enter here to become 3d10. This is the electron configuration of copper in a stable state, or the stable electron configuration of copper. Now for copper 1 electron, copper 1. For copper 1, it means that one electron will move from here. It will give out one electron to a non-metal. It has to give out one electron to a non-metal. And so copper 1, in copper 1 here, there will be only what? One electron. Then you call it copper what? 1. Why are we removing 1 from the 2 we have here? Please, why are we removing 1 from that 2 you have there? It is because for a metal to give out its electron, it will give it out from the outermost shell. And so the outermost shell of this electron configuration is 4s1. That is the last shell, the fourth shell. The third shell is inside the fourth shell, as we discussed before now. So the outermost shell is 4s1. shell, 4s sub 4s subshell is inside the outermost shell, which is the fourth shell, and so electron will leave from this. And when the electron leaves there, it is one electron, because here I said one electron. It will leave from there. That is about copper 1. But the question is this electron configuration stable? The answer is no. It has to obey the rule of P3, P6, D5, D10. And how can it obey it? This one electron will jump and enter here, making it stand. And so we'll be having it 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d10. This is for what? Copper what? 1 ion. This is the stable electron configuration of copper 1 ion, whereas this is the unstable aspect of it. Okay? Then we go for this zinc 2 ion. That means the zinc will be losing what? 2 electrons. Now, how do we do that? We go to this. Zinc has 30 electrons. It has a total of 30 electrons, whereas copper has 29. Okay, we go back to here so that we will not waste our time resketching. We now say this is 4s2 and 3d10. This is about 30 electrons. 4, 10, 20, 30. So 30 electrons. That is for what? Zinc. Now for zinc 2 plus. Zinc 2 plus means it will lose 2 electrons for the outermost shell. And the outermost shell we have is a fourth shell. And this 4s2 is a subshell in the fourth shell. And so 2 electrons will leave from this electron to be given to a non-metal. And so we now have it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s0, 3d10. That is for zinc 2 plus. It means that it lost the 2 electrons at its s orbital. It means that it lost 2 electrons that is meant to be at the 4s orbital. You notice now that a question can be asked from here. Which of these ions or elements have same stable electron configuration? Copper 1 plus and copper 2 plus have same stable electron configuration. So they obey this rule we just mentioned. Have it in your mind. Okay? So if you have a question in any of these questions we just solved, please feel free to what? Use the comment box below. All this square root and all have you. Check it and confirm it. Okay? Then, which of these orbitals is the most stable? That is question number 4. Which of these orbitals is the most stable? For you to know if this is stable or most stable, and if this is not, you have to get their energy. How you will get it from the energy of it is that you now say the one with lowest energy is said to be the most stable one. Okay. How do we calculate the stability? We say N plus L. Calculate their N plus L. N of this is 3. L of this is 2. Look at it. L of this is 2. This is their L. L of this is 2. And I say 2 plus 3, 5. 4 plus 1, P is 1. 4 plus 1, 5. 5 plus 1, 6. 5 plus, what is your D? D is 2. 5 plus D, 7. And so, we will say that these have the highest energy. These have the highest energy. And since it have the highest energy, this is least stable. Least stable. Highest energy. highest M plus L, that is highest energy. Now between this and the which one should be taken to be the lowest energy? The one with lower value of N is said to be the lowest N. So N of this is 3, while N of this is 4. This is lowest energy. Lowest energy, hence most stable. Hence most stable. So this is most stable because it has the least energy. The energy value is 5. This one energy is 5, but because the any value, this 3 is lower than 4, we take it to be the lowest energy. So the lowest energy is 3D, and so because it's lowest energy, we say it is the most stable. This one the highest energy, and so we call it the what? The least stable. So have them in mind as you watch it. Okay, we go to the last question. The last question says, calculate the element if N is 3, L is 2, M is 0, S is half. Wow. Now see what you do. Check the number of orbitals when L is 2. 2 times 2, 4, plus 1, 5. I will write what? I will draw 5 orbitals. Okay? Now, what this means is that elements, this is 0. The middle one is labeled 0, minus 1, minus 2, plus 1, plus 2. Yeah, that is about the magnetic what? Quantum number of 8. When L is 2, the M will be minus 2, minus 1, 0, 1, and 2. Now, electron will be entering singly first before what? Pairing. Okay? And it has to stop at M equal to 0. These are values of M. It has to stop at M equals to 0 in clockwise direction. Watch it. Singly. 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 This is M equals to 0. And this is clockwise direction. If here is minus half, if here is minus half, it means that it will get filled and start going for downward, and stop at M equals to 0. That is, if it is minus half, it will stop at downward spin at M equal to 0. Here will be filled. So it will enter singly, get filled, and start pairing, so that the downward spin, which is half, will be at M equal to what? 0. But they said it is plus half. And so what we do is that we maintain the question they ask us. We just stop at the question they ask us. Plus half means it stop at what? M equal to 0 via upward spin. Then that means the total electron we will have is 3. Now, L is talking about 2, that is d orbital. D. Then how many elements do we see here? 3. Then what is your N? N is what? 3. N is 3. And so what you will do is that you will say the elements will be gotten this way. You will be writing 1s2 and stop at 3d. 2s2, 2p6, 3s2, 3p6. Then you now also have 4s2 and 3d3. Okay? How many electrons? 1, 2, 10, 20, 23 electrons. Which element has maximum of 23 electrons? Which element has 23 electrons? 20 is scandium, 21 is scandium, titanium. Okay, so this is what? Vanadium. Vanadium. So the element we are looking for here is called vanadium. That is the one with 23 electrons. That is the one with what? 23 electrons. Okay? So that is how to solve these questions we have for today on quantum numbers. Thanks for watching the video. Please don't forget to click like button, comment, click share to your friends. Yeah, I appreciate. For the one you have done for me, share it to a friend watching my videos. I appreciate. Thanks very much.